Today we are going to move beyond the one sample t-test and talk about the comparison of two different samples, two different populations, to see whether or not they are the same. Or, really more interestingly, are they different? So we have a couple choices when it comes to the parametric tests, comparing two samples. One choice is to use a paired comparison, and the other choice is the unpaired comparisons. We are going to start by talking about the paired comparisons. And so let's do this by running through an R script and running through an example. In paired designs, two observations are identical in almost every way except for the categorical variable. So one pair is from one group, or one member of the pair is from one group, and one member of the pair is from a different group. For example, an individual observed before and after treatment, or observations from an upstream and downstream portion of the same river. The equation for a paired t-test is very simple, and it looks a lot like the one sample t-test. It is d bar, the mean differences, minus the hypothesized null mean difference, or mu sub d naught, and that's typically 0, and we divide that by the standard error of d bar, or the standard error of the mean differences. So let's look at an example here, looking at mice weight data from before and after some treatment. This is from the Deuterium library, so we have to install that if you haven't done that already, and we have to call library Deuterium. We then call the data mice2, and as you can see, we have a bunch of mice, and they have weights in milligrams before and after treatment. So our hypothesis is that there's no difference between the weights before and after treatment. And our alternative hypothesis is, in fact, there is a difference between before and after treatment. We can rewrite that as an expression of mu d naught, and therefore our null hypothesis is that mu d naught equals 0, and our alternative is that mu d naught does not equal 0. Our observations are before and after, so we make vectors of those two columns. We calculate the mean differences, or d bar, and that's simply the mean of our before vector minus our after vector. We take the standard deviation of the difference. We calculate the number of pairs, and since the number of observations in before and after are the same, we just need the length of one of those vectors. Here I chose before. And then we need our null hypothesis, which in this case is 0. We calculate the standard error of our mean differences by taking our standard deviation of the mean differences divided by the square root of our n. We then calculate our paired t-test statistic, and that is written out here, and we get an answer of negative 25.54 or 25.54 if we consider the absolute value. We then need to calculate a t-critical value to compare to our test statistic, and so we use the qt function with a probability of 0.05 divided by 2, because this is a two-tailed test. And we include our degrees of freedom, which is the number of pairs minus 1. And we get an answer of negative 2.262, or 2.262 if we consider the absolute value. Since 25.54 is much larger than 2.262, we reject the null hypothesis, and therefore we have evidence that there are differences in the means between the before and after. We can run a paired t-test really easily by using the same t.test function that we use for the one sample t-test, but we include our before vector, our after vector, and we indicate that paired equals true to tell R that yeah, we're doing a paired t-test. We get our outputs, and as you can see, our t value makes sense, it's the same one we calculated, and it's giving us a p-value, which is really, really, really small. And so since our p-value is less than 0.05, we reject the null. And so that is consistent with our comparison to the critical value from the previous step. The assumptions for the pair t-test are that all pairs are chosen at random and that the differences between pairs are normally distributed. You can check that by taking the differences between pairs and looking at a histogram.